8. So today we're going to be covering graph stuff, pretty much all of chapter 6 and 8, all at once. So this is the part of the course where the acceleration is going to kind of affect us a bit, but I'm hoping the main takeaways will still be clear. So in lecture, we're not going to go through every algorithm in like intense detail, but we're going to focus on the main ideas and the main things you need to know about them. In particular, we're going to use these ideas mostly as tools for graph reductions. So for the most part, you don't really need to be a master at the theory of these things, but you should still read through the book and understand them, of course. So that's the main thing we're going to go through today. Graph reductions are just a generalization of DP. It's a very general technique. You can use it to solve pretty much everything I could think of. It's really amazing, but it's also, with such power, it's very hard to use when you're first starting. So we're going to focus on graph reductions for the most of this week. That'll be the discussion as well. Will be on graph reductions. All the videos I put out later will be about graph reductions. So hopefully you'll get plenty of practice with it. If you're wondering why there was no greedy video last time, I decided not to upload a greedy video. I didn't think it'd be very useful because most of the problems are pretty simple. So instead I uploaded like a practice problem type thing of greedy under discussion. And what you should do is just read through that, try the problems on your own, and then I upload the solutions so you can check your work too. It's just a bunch of different greedy algorithms for solving scheduling. We talked about the finish first algorithm last time, and so those are just different versions of various complications that you can take a look at. Okay, so that's the outline for today. We're going to roll through the first 4 topics pretty fast, so if there's any questions, please, you got to be assertive in stopping me, because otherwise I'm just going to roll through them. Any questions? Okay, so then we're going to start with some DFS. So we talked about DFS and BFS before, but now we're going to look at some generalizations of them. So the main difference here between normal DFS is this pre-visit of V and post-visit of V. So we talked about pretty extensively when we were doing tree dynamic programming that we want to do post-visit or post-order traversals or pre-order traversals. So this is how you actually do it, is instead of directly having like a for loop that does a traversal, you're doing a DFS, but then you're plugging in your subproblem evaluations here. So for DP, this is where you plug in the subproblem eval for V. And similarly, you could do a pre-order traversal. Those are things that happen before the node is visited. So at the very beginning, if you want the nodes visited from top down, you would modify pre-visit and do a pre-order traversal. So pre-order looks like this. You hit parents first. That's for pre. And for post, that's what we've been doing all semester. That's where we're doing more of the bottom up, hit children first. And in general, you could have really complicated situations where you actually want to do both. And so this template gives you that option. Otherwise, pretty straightforward. So where this is going to get complicated is when we use specific versions of pre-visit and post-visit. But first, I just want to draw your attention to something. So I mentioned when we were looking at chapter 5, when we look at connectivity of graphs, a connected graph, it's different for undirected and directed graphs. So we mostly focused on undirected graphs till now. Now we're going to focus mostly on directed graphs. So I just wanted to point out that these 2 graphs here, these are both connected if they were undirected, because there's an edge between all the nodes. But because each edge has an arrow, it's not really connected. If you started at this node here, you could never get to some of these other nodes. not everything would be reachable. And similarly, if you started at this node, you would hit all these things. You would skip these. So this is just to show you that connectivity is different in directed graphs. It's not enough that there's edges everywhere. You have to have the right orientation of the edges. The arrows have to be going in the right direction. Otherwise, here's an example of what DFS would look like if you started from two different nodes, specifically this node and this node. And just like normal with DFS, you start, you just keep, it's almost greedy really. You're going as far as you possibly can, then you backtrack and do the same thing again. So those are some DFS trees. And now, because these directed graphs don't have to be connected like before, we can't just call DFS from a single node. We have to call DFS from every node if we want to guarantee we hit everything. So this is just a wrapper function that will throw around DFS. And all we're doing is just calling DFS for every unmarked vertex. So we start, maybe we hit a bunch of nodes, like here, but some of them are missed. So then the loop, it's going to try all the other ones. It'll find this unmarked one, and then it'll do its DFS, and all those will get marked. So that's the thing on the left here, is just a loop. Now you can also do this by just making a new graph. So that's what's on the right here, is you can take your original graph G and just add a new super source vertex that connects to every single node. And then if you do a single DFS starting at this S node here, well, it's going to implicitly do this loop. It's going to have the same exact effect. You'll end up hitting every single connected subpart. The only other difference is these pre-process functions. You can think of this as initializing stuff for DP. So you have these post-visit and pre-visit here. Those might have some arrays or tables that you're filling, and so obviously you need to initialize and construct those arrays at the beginning. So that's where you're doing that, is in the pre-process step. Okay? So any questions about any of this before we move on? Hopefully it's mostly review. Okay, so here's slightly newer stuff. So we're going to do the same thing again, but specialize pre-visit and post-visit. So now pre-visit, what it's going to do, it's going to update a clock parameter, so it increases our time step. It's also going to set the value of v.pre to be that clock step. So for each node, we're going to keep track of when we visit it for the first time. So this is the first visit. And we're going to also keep track of when we leave that node, or at least take it off the recursion stack, to be precise. So we're going to keep track of both these things, pre and post. And the idea here is keeping track of these pre and post will give us more information about the structure of the graph. So before, we just kind of marked the vertices and said, has it been visited or not? But by being precise with these timestamps, we'll learn more about, the structure of the graph and how everything's connected. So in particular, we're doing this to define pre-order and post-order traversals. So we know what a pre-order and post-order is for a tree. We've done that in the past. But for directed graphs, they could have cycles. So what does it really mean to do a pre-order or a post-order traversal? So if you remember topological orders, that's a very similar concept to this. But this is even simpler than topological orders. Okay, so we're going to use this clock to define these things. And ultimately, the idea here is if you sorted all the vertices based on their pre, that gives you the pre-order traversal. If you sort them based on their post, that gives you the post-order traversal. So if you sort the nodes by pre, that gives you the pre-order traversal. And similarly, you can do the same thing with post. And so this way, even though there's cycles, we can still pick an ordering of the vertices that we could call pre-order, even though it's not a tree anymore, and it might not have a tree-like structure. Okay? So as I mentioned, using this clock, it's going to tell us a lot of information, way more than you might expect just from a clock. So what exactly will it tell us? So here's a really simple thing it tells us immediately. If I tell you that U started, or we entered U, before we entered V, and I told you we exited V before we exited U, well, that implies there's a directed path from U to V. And I'll denote that with the wavy arrow. Or we can also say V is in the reachability set of U. So there exists a path from U to V. So that's one condition. There's actually 4 of them, so I didn't list them all. They're not super important to know the mathematical definitions, but you can create all these different subcases to figure out how these different nodes are related. So in particular, one key theorem here is let's look at the interval. So fix a V and look at the interval where it starts and when it ends. And that's shown in the picture above. So for E starts at time 23 and it ends at time 32. So that's its interval. And one cool thing about this algorithm is the intervals are always nested or they're disjoint, guaranteed. You'll never have like partial overlaps. So something like this can never happen, which is really surprising. In particular, one other thing you can infer from this, if you do have nesting like this, so B is contained in A, F is contained in B, and so on, that means DFS starting at A called B, and it eventually caused F to be called. So if you think of DFS as a physical walk where you're starting at A, you took an edge to B, then took an edge to F, this nesting says that if you started at A and my interval is nested inside of A's interval, eventually we'll walk down nodes and hit one of those in there. So for example, for C, we eventually hit C by walking down the path from A. This could be any arbitrary, complicated graph, doesn't matter. Okay, so that's physically what's happening. That's the picture associated with these intervals. Okay? And so there's 2 main cases. So we have the nested case, and that's, like I said, you started at A and you ended up hitting all those nodes. But you could also have disjoint intervals. So E starts after A has already ended. They're completely separate. And if they're completely separate, intuitively, this says they're in 2 different directed components. So in the picture here, we start at A and we walk down the tree. We hit everything we can hit in the graph from A. But we don't hit everything. So we have to restart at E, and then we hit everything that you can reach from E. And you get these 2 disjointed cases. And the disjointedness can happen anywhere. It's not exclusive to like the top of the graph. So down here you have D and L are disjointed. That symbolizes that we went to D, which is like a leaf now. We pop back up to H, so we're in DFS of H. So in DFS of H, we went to D, we came back, then we went to L and did some other stuff, and then eventually we came back. So D and L are kind of in parallel, in a sense. Okay?
What do the different colored arrows mean?
Oh, we'll get to that in a second. Yeah, good question. So before I get to that, let's first look at the resulting pre and post order. So this one's the pre-order, and this one's the post-order. So the pre-order, you can actually read it just from looking at the picture. The first thing we visit is A, it starts first, then B, then F, and so on. And the very last thing we visit is M. And in the picture, you can see that's exactly what happens. On the other hand, the post-order, these are the things that end last. So the very first thing is going to be D, because that's the first thing that ends. The next thing that ends is going to be K, and so on. We trace through this, and the last thing that ends is E. So it's at the end. Okay? So if we're doing dynamic programming on this graph, the very last thing we would hit, or basically where the base cases start, would be at E, because it's the very last thing in the traversal. So we'd compute the stuff at E and then propagate that forward into the graph. Okay? So the intervals have a lot of other mathematical properties that I won't go too deep into, but they're interesting if you're interested. Okay, so before I talk about the color of the arrows, any questions? Nope. Okay. So, we can classify edges in different ways now. The first one's called a tree edge, because it's going to be present in the DFS tree. So these are in the DFS tree. And tree edges are the simplest case. An edge UV is a tree edge if DFS of U directly called DFS of V. So when we're looping over next possible edges, that was one of the ones we ended up going down. A back edge means we found a directed cycle. This isn't like the mathematical definition. All of these are defined based on the pre and post clocks. But intuitively, when you see a back edge, that's what you should think of. It means we formed a cycle. We're going back to something we already visited. A forward edge is the opposite. That means we're going forward in the future. So in this picture here, B to C would be a forward edge. Because eventually we get to C, but it wasn't because we used this edge. We used other edges to get there. So in other words, DFS of U eventually causes DFS of V to be called, but it doesn't directly call it. And lastly, a cross edge. This one's the weirdest one. We'll see a picture of it though. And this means we found an undirected cycle rather than a directed cycle. So instead of going back in time, touching a node we've already been to, we're touching a node that's kind of across from it. So it'd be an example of like D and L. If D and L had an edge between them, that would be a cross edge, because they're kind of in parallel. Okay. So that's just in words. Here's a picture. So here's the DFS tree. We started at S, we moved to T, we moved to U, then we moved to V. There's nowhere else to go, so we backtracked to U, moved to W, and then we were done. So if that was the order of our DFS, then all these things in black are called tree edges. Those are the ones we physically walked down while we were moving through the tree. So that's how you want to think of it, is you're physically like walking down this path. Now the orange one, that's a back edge because you're going back up the tree. So that's why it's called that. Like physically you're going up the tree. A forward edge means you're skipping down, you're going into the future. And the cross edge, if you draw it like a tree, then it's literally a cross. It's an edge that crosses the two sides of the tree. So that's what it looks like. if you reorient this as a tree. Now in the original graph representation, this is what it looks like. So here the green edges are the tree edges. That's our DFS. Back edges are the orange, blue edges are forward edges, and cross edges are the gray. Yes?
Can we say S to the U as a forward edge?
If there was an edge S to the U, it would be forward. Yep. And then again, if we looked at the interval notation, you can kind of predict this behavior. So because S, T, U, they're all nested, but these two are disjoint, you know the V and W edge has to be a cross edge because they're disjoint. Any edge that goes down from S to T, T to U, these are all tree edges. Any edge that went back, such as U to S, that had to be a back edge. This one's cross. And forward edges would have skipped an interval. So that's what it looks like in the interval notation. And then in the original, the more complicated example, you can still do the same thing. Here the green edges are literally what we followed when we're doing the DFS. Some order. And then from that order, we can figure out, okay, this is a cross edge. Because when we finally hit this edge, these two things are disjoint intervals. You can see the back edges because they go back to a previous thing we've already hit. And the forward edges are things that jump to the future. These are things we'll visit much later in the DFS, but there is an edge to it if we chose to do that. Yes?
So, is this, are all of these arrow types, or trends, relations, or whatever are they all just trying to classify all the arrows that weren't in the interval that we had?
So the dotted edges are things we did not physically walk down in our DFS. The bold green ones are the ones we physically used in the DFS.
Right, so we're just trying to make sure that all the connections are classified.
Yeah. So this will classify every edge as one of these four types. So why do we care about these different edge types? So tree edges are the most obvious because that's what you're actually computing in a DFS. Back edges are really important because in the very next topic, our goal is to find cycles. So that's what those are used for. Forward edges and cross edges secretly do a lot of stuff for us. Oftentimes in an algorithm's problem, you'll have to compute some really strange thing, and it'll actually be equivalent to find all the cross edges in your graph. So these aren't immediately useful for DFS itself, but they're usually pretty useful in applications. And I won't say more about that today, but you might see that on, say, homework. Let me just say one more thing about cross edges. So here I said it means you found an undirected cycle. That's because if you looked at this picture, this isn't a directed cycle. You can't follow it in a loop. You get stuck. But if you erased all the arrowheads, then it is a cycle. So that's why I called it an undirected cycle. And that's what cross edges are doing. Yes?
Can we see all of these in the interval notation? It feels to me like tree-violating edges are hidden there or something.
So for the interval notation, you could see them if the edges were drawn on the intervals. So by looking at the intervals, you can infer what edges will be what, but you need to know what the edges are. So this hides what edges exist in the graph, other than the tree edges. You can always read off tree edges because they're just S goes to T, T goes to U, etc. Every time you go down, it's a tree edge. But if I drew the arrows for you on top, like here, then you can always figure out, okay, this has to be a back edge because we already visited S. This is a forward edge. That's a cross edge because they're disjointed. Yeah, and the picture would be T to V. It's not drawn to scale. Yeah. Okay. So I'm not going super rigorously into how you define these based off the clock parameters, but I hope the idea is clear, because that's all we really need for the next topic, which is cycles. So we talked about directed acyclic graphs before. As the definition says, they're directed, they're acyclic, and they're graphs. So here's a representation of one of these DAGs. In particular, these green nodes are the sources. So remember, a source is any node that has no ingoing edges. It only has outgoing edges, or no edges. Sinks are places where you end. They only have ingoing edges. So once you're in a sink, you can't leave. You're kind of stuck. If you're at a source, you have to leave. You can never get into a source. Everything else is intermediate. You could either leave or you can enter and you can leave. Sources, you can only leave. Sinks, you can only enter. Okay? And DAGs are used all the place, everywhere, such as in DP. So if you remember in DP, what we're really doing are DFFs of dependency graphs, where the dependency graphs are DAGs. And remember, if the dependency graph is not a DAG, then you'll have an infinite loop. So that's why DAGs are important for DP. Every single DP algorithm is really a DFS over a dependency graph. So obviously we care about if something is a DAG or not. There's plenty of other applications besides in dynamic programming where DAGs are better. Typically, DAG algorithms are way faster. Like every DAG algorithm I've ever seen is like O of n time, whereas the more general ones could be O of n to the fourth for almost the same exact graph, but just a couple extra edges. So DAGs are a super, super useful object to have. So now our question is, we have a graph. We don't know it's a DAG. How do we figure out if it's a DAG? How do we detect these cycles? In particular, this is kind of equivalent to checking if an algorithm that's recursive will infinitely loop. If there's any kind of recursive call that calls itself, well, that's going to loop infinitely. So that's also the kind of thing this kind of algorithm will check for us. So it's very useful. So here's the algorithm. It might look kind of scary, but it's really just DFS. Check for back edges. So what's happening here is we're going to start by assigning every V a status that can be new, active, or finished. So new means we have not touched it yet in the DFS. Active means we have touched it, but it hasn't finished yet. So we call DFS of V, and maybe DFS of V is still going. It's creating more and more recursive calls. We haven't taken it off the recursive stack yet. And then finished means we're about to take it off the recursive stack. We visited everything that V can reach, and now we're done. So at this point, we've visited everything in the reachability set of V. Okay? So other than that, this is just normal DFS. If V.status is new, that's the same as it's unmarked. If it is, then we're going to do DFS, but specifically with a check to see if there's a cycle. And if there is a cycle, which means this thing will be false, then we return false. So if we found a cycle that touches V, then we found a cycle in the whole graph, so we output false. Otherwise, if every single path does not end in a cycle, we return true, because that means it's acyclic. So equivalently, what this is doing, if there's no back edges ever, then return true. And obviously, if you have a cycle, you have to have a back edge, because any cycle is a directed path, some directed path with an edge at the end to complete the cycle. And that edge at the end will always be a back edge. Okay? So then over here, everything else is the same as normal DFS, except now we check. For every edge v to w, we check is W status active. If it is active, that means V here is that W, so actually let me rename it so it matches. So this is W, this is V. So if W is active, that means it's already on the stack. We're currently in a recursive call that came from DFS of W. And now we found an edge that goes back to W. So W is active, which means we're currently visiting it in a sense. And now we found this edge from V back to W. So that's going to form a cycle. In other words, this edge is a back edge. So if we find that W status is active, that means we just found a back edge, and so we're going to return false because we found a cycle. Otherwise, if it's new, we haven't visited it before, it's not a back edge. This is just making a tree edge, and then we recurse. And again, if we never find a back edge here, then we return true. And the key idea here, as I just alluded to, is if W is active at the same time V is active, then we're in the nested intervals case. So W active means that W.pre is less than V.pre. And you can also argue it ends after 2, so it's nested. And we know if it's nested, that implies there's a directed path from W to V, and so that directed path plus that last edge gives you the cycle. So that's the idea, but you can also formalize it using these definitions of pre and post, using the clock parameters. And that's why these clock parameters are so cool, because they allow us to prove things formally about statements that seem intuitively obvious. So intuitively, if we revisit something that's already marked, there's a cycle. But to prove that formally, we need this clock framework. Okay? So the running time is going to be the same as DFS, just because we added a couple if statements and stuff. Not a big deal. So it's linear time. So we can really quickly figure out if a graph has a cycle or not. So any questions on this? And this is not the only thing you can compute using the DFS with pre-visit and post-visit. You can figure out a lot of stuff about a graph just by running the modified DFS. This is just one useful example. Okay, cool. So now we're going to get to the crazy stuff. Strong connectivity. So we've been talking so far about how in directed graphs, you don't really have the same kind of component structure as in undirected graphs. Starting at one node, you could end up at some other node. You can follow arrows to get to V, but maybe there's no path back. Whereas for an undirected graph, it's symmetric. Any path from U to V is also a path from V to U. So for connected graphs, it's symmetric, but not for directed graphs. So figuring out what's reachable from what is a little more complicated. So we need this new definition of components. So instead of a component just being everything that's connected, it's now going to be everything that's connected in both directions. So a strong component of G, this is just some subgraph, G prime, such that for every pair of vertices in the subgraph, U is reachable from V, and V is reachable from U. So if we drew like a picture of one of these, we have, say, this graph. This could be an example. Maybe there's other stuff too. But this chunk right here would be a strong component. Because starting from any node in that component, you can reach all the other ones in the component just by following that cycle. So you can just follow the cycle as many times as you want and keep hitting every node. So for every fixed pair, U and V, maybe this U and this V, there exists a path that goes from U to V, and there exists a path from V to U. There's both paths in this graph. And that's what a strong component is. So it's the same thing as components in undirected graphs, except now you have the extra condition that you have to reach in both directions. There has to be directed paths in both, from one to each. Okay? So then for a specific node V, we can think of what is the component of node V. So before, you could figure that out just by running a whatever first search from V, or a DFS if you prefer, whatever search you want to do. And everything that was marked would have been the component. So before, everything marked in whatever first search of V was its component. And for strong components, it's actually not that hard to figure it out. So you can still use whatever first search, but you just have to do it twice. So you do it once to compute the reachability set of V. So this is just everything V can reach. Then you also have to compute everything that can reach V. So reach inverse, that's what the -1 stands for, that's the set of all U that have a directed path to V. So the intersection of both of these sets is exactly the strongly connected component of V, because by definition, it's everything that V can reach and everything that can reach V. So that's what that is. Now to compute the first part, that's just literally WFS of V, or DFS of V, whatever you want to use. Now to compute this one, what we can do is call whatever first search in the reverse graph. So what's the reverse graph? The reverse graph just reverses every edge. So if you have an edge U to V originally, you're just going to flip it to be V to U. So pictorially, maybe our graph looks like this, and then this. Then in the reverse, it's going to look like this, this, and this. Okay? You're just reversing the direction of each edge. And also notice that the reverse of any DAG will also be a DAG. If there's no cycles, reversing all the edges aren't going to make a new cycle. Essentially, the structure of the reverse graph is very similar. If you looked at it on paper, they look almost identical. You just flip the arrows. An important point is you can find them fast. So you can compute the reverse graph in V plus E time. I urge you to think about why, just messing around with the adjacency list. But you can do it fast. So you can compute strongly connected components for a single component fast by using 2 calls to whatever first search and by building the reverse graph. Okay? So any questions so far? Yes.
Can we take it for granted that reverse of a graph exists and just call it that and refer to it without having to build it ourselves?
Yeah, for sure. You can just say use the reverse graph. Just make sure you take into account the running time. Because if the whole problem is reverse the graph, then it's not constant time or anything. You still have to take into account how long it takes. But yeah, you can throw these things around, and I recommend you do. Please do throw the reverse graph around. They're very useful. They're surprisingly useful. Like, this doesn't seem very useful when you first hear it. It just seems like mathematical, like, of course you can flip edges, whatever. But this thing is so useful, it's surprising. Okay, so everyone clear of what strong connected components are? Well, here's a picture of one. So far we've talked about a single component, but what if I wanted to get all of the components? So here, we're going to create something which is called the strongly connected component graph of G. It's sometimes called the metagraph or the condensation graph, whatever you want to call it. I'll just call it SCC. And the idea here is you're going to take all the strongly connected components. So everything here these blobs are every strongly connected component. So notice here, this node E. This node E is a source. And so the strongly connected component of E is just E, because the only thing that can reach E is itself. By definition of a source, nothing else can reach E. So E is all alone in its component. And so what we're going to do is we're going to take all the components and collapse them into a single node. So here the ABFG turns into this blob. E turns into a blob. All of them turn into their own blob. And then we're going to collapse parallel edges. So notice here, you could have multiple. So for example, G has two different edges to the yellow blob, but there's not two edges here. We're just going to merge them into a single edge. Okay? So we replace every component of G, every strong component, with a single vertex, these giant blobs, and then we merge any parallel edges. So any parallel edges that would be created, like this, we just ignore it. We merge it into a single edge. And the cool thing here is this will always be a DAG. And so you can do DP on it. So what this really is, it's a hack to DAGify any graph. And this thing is super useful. So you can take a very complicated graph, maybe you want to solve some problem on it, and sometimes all you have to do is create the DAG version, the strongly connected component graph, and then do dynamic programming on it. You can because it's a DAG. And this is surprisingly used all the time. So strongly connected components are extremely useful. In a sense, each of these blobs is summarizing connectivity information. So you could think of this as maybe these edges represent roads and the cities, and the nodes are cities. Then each blob you could think of as cities where you can commute really fast. So there's sub-collections of a city that are really fast. So if you want to find the shortest path, you can always find the shortest path in each blob because by definition, they're very clustered. So that's easy. So all you really need to do is navigate the outer structure. And you can do that faster than traditional shortest path algorithms. So that's one example of where DAGifying is very useful. But it's not the only place it's useful. It's useful everywhere. Yes?
Can you elaborate that you can do DP on it?
Yeah, so remember we can always do DP on a DAG because there's no cycles. So in this graph, there are cycles, so we can't do dp. But if we dagify it, we can do dp on this graph. And maybe doing dp on this graph, depending on what your subproblems are, that might translate into a solution for whatever you originally wanted. So if you don't really care what happens in the intermediate clusters, you just really care about the outer stuff that's happening to the overall connections, then solving your problem using dp on this DAG will be much faster than solving it in the original, which has all these complicated cycles and other structures. But there's a lot of different ways you can do it, so I'm leaving it vague for now, just so when you're on a homework and you're like, what do I do? Maybe you'll try it. Okay. So now the hard part. How do we actually create this graph? So in principle, we can always dagify a graph. We can always find the SCC graph. But like, how do we actually compute it? Can we even compute it fast? It sounds really complicated. So one thing you could do is for every single node, so for every node V, construct the component of V. And we know how to do that, right, by doing two whatever first searches, one in the reverse graph, one in the normal graph. So we could do that for every single vertex and then kind of merge the ones that are the same. So we can just construct this for every vertex and do some extra stuff to create this graph. But if we do this, it's going to be O of V times E. Because for every node, we're doing a search. And this is pretty slow. In the worst case, that's going to be like V cubed or N cubed, where N is the number of nodes. But I claim you can do this in linear time, very fast. So there's a couple of key observations that are based on the clock ideas. So the first idea here is it's easy to figure out a sync component, given a sync node. So why is this? So remember, a sync component, it's just a sync in the SCC graph. So for example, P here is a sync component. And now what's cool about a sync component is it has no outgoing edges, by definition of being a sync. So everything in a sync component can only reach themselves. They can't reach other components. So in particular, any search of some sync node will exactly be the sync component. So you can do a single search to find the whole sync component. You don't have to worry about accidentally going farther into other components, because there's nowhere else to go. You're at the end. So that's the first observation. If I gave you a sync node, you can tell me the sync component. So let's say we did that. I gave you a sync node. Then what we can do is compute the sync component using the whatever for search, remove it from the graph and its ingoing edges, so things that go to the sync, and then we can recurse. So the idea here is once we've eliminated that sync component, this becomes a new sync because we've removed those outgoing edges. So it no longer has outgoing edges, it's a sync. And so we can recursively, again, apply whatever for search in this component to figure out the whole component, remove that, and continue. So moving backwards will construct the entire graph. We find a sync, remove it from the graph, recurse. Then we glue them all together. So that gives us a recursive algorithm to compute the SCC graph. And here's the pseudocode. So we take any vertex in the sync component, we basically do a search over it. And for every node we find, we're going to label it the same label, count. So the way we're going to keep track of the components is labeling them each a different label. So before we used like a clock, now we're just going to use a count. You could think of these as assigning a different color to each component, all the same thing. Then we remove the component and its incoming edges. So this is almost an algorithm. It's not an algorithm because we don't know how to do the step in bold red. How do you actually find that vertex? I don't know. But if you could do it, then this is just a simple recursive algorithm to create this graph. Okay? Now I've also put a question mark here because how do you actually remove the incoming edges? This depends on how you represent your data structures. So if your directed graph has, for every vertex, a list of in and a list of out. So if you have in and out for each v, and it's like, these are all the in edges, these are all the out edges. If you had that, then this is super easy. You just read through your list of in edges, and you can figure out which edges to remove from the graph. But if you only know the out edges, if your adjacency list using a standard adjacency list, then this is a little more complicated. You can still do it in linear time, but you should think about how to do it. Or just say, I'm assuming we add in an in list, and then it's obvious how to do it. So I just want to emphasize here that that last line is not necessarily fully specified yet. There's still a couple things you need to say there to make it a full algorithm. Okay, so this is the template. So the next thing to notice is it's easy to find a source node. So we want to find a sink node, but we know how to find source nodes. How do we do that? I'll tell you later, but believe me, we can do it. So the last observation is that a source node in the reverse graph is a sink node in G. So once again, the reverse graph comes in to save us. If you just flip all the directions of the arrows, anything with no arrows leaving now becomes something with no arrows coming in. So if you had some sink S, then in the reverse graph, it'll look like this. So it becomes a source. So now what we could do is we can construct the reverse graph, find a source node, and that source node in the reverse graph will actually be a sink node in the original. And then we can plug that in here. So this will just be the source node in reverse of G. Okay? So that's pretty much all the steps. We can successfully run the whole algorithm. So I said we can find source nodes, so how do we do that? This is how we do it. Once again, post-ordering, super useful for no good reason. So the last vertex in any post-ordering is a source node, somehow. So in particular, if you ran like a DFS and you just read off the very last node in the post order, that's going to be our source node. So one more thing is this is going to be the last node in the post order of G. So notice we're doing two things here. We're searching through the reverse graph, and we're searching through the original graph. You're kind of simultaneously walking through the reverse graph and the normal graph. So if you're wondering why the last vertex in a post ordering is a source, here's a quick proof sketch. So here, if you remember that graph above, E is the thing that ends last. So E is going to be a source. So why is E a source? Well, the idea here is, notice everything is nested in E. So everything else is disjointed. Those are separate, we don't care. But everything here is in E. So they're all reachable from E. So intuitively, E is kind of a source because everything is coming from E. We started at E and we kept moving down. Okay? Now, formally to prove this, we're going to do it by contradiction. So if this was not a source node, there must exist an X. So here we claim this is a source component. And so E is a source node. So if it's not a source node, because this isn't a source component, there's a different component with a node that comes in here. And in particular, because the component's connected, that implies it can also reach E. So eventually, it'll reach E. So there's some path from X to E, assuming this is the case. But if there's a path from X to E, we know by the post-ordering, X had to end after E. Because X would have called this path and eventually have hit E. Or, so either it's the case in orange where X ends after, and they're nested, or we called whatever for search on this component first, and so we'll get the disjointed case. So the other option is E is here, and after we finished E, we call X. But then it'll be disjointed, and this will still end later. So in either case, whether it's disjointed or it's nested, it must be the case that X ends later. But that contradicts the fact that this was the last vertex in the post-ordering, which means it ended the latest. Okay? So I'm not giving you all the details of the algebra with post, because you technically are comparing like pre and post. But intuitively, the picture is telling you, it's capturing that same information. We know they're either nested or disjointed, and in either case, X will end later. So any questions on that? Yes?
I just did not understand pseudocode. This is a pseudocode like for calculating the complete DAG of SCCs, right?
It's the idea. It's not the pseudocode.
Okay.
If you want the full pseudocode, it's disappeared. There it is. That's the full pseudocode. But the main steps are these two phases here. One step where we're doing a DFS in the reverse graph. This is so we can find the sync components, the sync nodes. And in fact, you can find them all at once. You don't actually have to compute them one at a time recursively. So this is just a one pass find all the sync nodes. And then phase two is you're going to DFS in the original graph to find all those components and then remove them. So that's the full pseudocode. It's kind of complicated, which is why I didn't make this bigger. But the main ideas are you're finding the sync component, you remove it in recurse.
One more thing, the dive running time of finding all these SCCs, you've told that it's order VE.
The brute force simple way, yeah.
Yeah, but should ideally be V times V plus E, right?
Yeah.
Then why do we like drop the first component, V square?
Because traditionally you assume E is larger than V, so you'd kind of ignore.
Then why don't we like drop it like when we are like calculating the running time for like DFS or WFS, which is order V plus E? Why don't we just call it order E?
Yeah, sometimes they do. Yeah, I agree. So the book's kind of inconsistent. Sometimes they say OV, sometimes they say OV plus E. It usually depends on the context. So for things like shortest paths, you ignore the V terms because in shortest paths, usually you have like lots of roads. So usually the edges are bigger in shortest path contexts. But for things like trees, the edges can actually be smaller. So then you would want to take both into account. So typically it's context-based. For purposes of this course, you can always assume E is the larger one. That's cool with me. You don't have to be super precise with it. But generally, from the context, you can determine which one makes the most sense. So yeah, the final time of this algorithm is V plus E, just because we're doing a DFS in the reverse graph, DFS in the original graph. We're doing some constant time stuff in between. So overall, we get a linear time algorithm to compute the SCCs. Cool. We're on schedule. That's incredible. So any questions about this so far? For the most part, you don't need to really have an incredible understanding of how this algorithm works. The important part is you understand strong connected components and are able to use them, rather than can you build one. The building's kind of done for you. That's the theory. But it is a cool algorithm, so I urge you to at least think about it. Look at it in the textbook. It's also a really neat example of how these clock parameters can help you calculate really advanced things. You'd think some clock parameters kind of, at best, just giving you a tiny bit of information, like whatever, but it ends up allowing you to compute a pretty sophisticated structure in your graph, and doing it quickly too. So these clocks are really useful. So any other questions before we move on from DFS stuff? Okay. So now shortest paths. So we've already discussed shortest paths quite a bit. And specifically, we've looked at the DP algorithms for it. So in, I think, lecture 5, we looked at doing DP on a DAG. And you do that with this recurrence. So remember, the idea is if you're at the starting node, S, then the distance is 0. Otherwise, you look at all possible ingoing edges into V. All possible ingoing edges. And you're going to pick the best path recursively, which will be the distance to get to U, and then the weight of moving from U to V. And you're just going to try all possible incoming edges. So that's what we did before. That's how you do it for DAGs. Now, we've also discussed BFS before. And BFS is essentially doing shortest paths on unweighted graphs. We've proved that before. And actually, BFS is really a greedy algorithm, if you think about it. In BFS, you always move one step away. And every time you move one step away, you immediately update the distance. Immediately, you're saying the distance of V is the distance of U plus 1. Where this is U, this is S, this is V. You don't really consider other paths, right? You're not saying, well, maybe this other path is better. You don't even think about that. The second you hit V, you update its distance and you never touch it again. So really, you made a greedy decision to permanently change its distance to the first thing that looked good. Whereas for the DP one, you're trying all possible edges, and you might even change the distance of U over time. It could fluctuate. So that's the difference in these two cases. Now we're going to talk about two more advanced versions. So for positive weights, these are the weights, by the way, these numbers on the edges. If these are all positive, the algorithm you always want to use is Dijkstra. You should pretty much always use Dijkstra if the weights are positive. There's no good reason not to. It's a really good algorithm. Otherwise, if the weights are not positive, you want to use this algorithm called Bellman-Ford. In Bellman-Ford, we actually already went through the DP version of it, but we'll discuss it again in a different version. So just to remind you what the goal of the shortest path problem is you're given a fixed start node S, and you want to compute the shortest path from S to every other node. So you're creating this distance function d of v for every other node. And you can also view this as computing a shortest path tree, because if you combined all the shortest paths and just took a union of them all, it's going to look like a tree. So here, the shortest path from S to this node, S to that node, etc., it's a tree. There's no cycles or anything. That's something you can prove in general. So here's an example of some shortest paths. And now I want to contrast this to minimum spanning trees. So if you remember minimum spanning trees, the idea is you have an undirected graph, and you want to pick edges that form a tree with minimum total weight. And it's similar to shortest paths, but the difference is for a shortest path, you have this root node S that you have to start at, whereas a minimum spanning tree doesn't have a root node. There's no preferred node. So here, starting from S, the fastest way to get to this node is 8. The alternative would be 5 plus 3 plus 2, or 5 plus 10, both of which are much larger. They're both at least 10. So you definitely don't want either of those paths to be your shortest path from S to that node, which I'll call U. On the other hand, if we're looking at a minimum spanning tree, you don't really want to take that edge 8 because it's really big. You'd prefer to take all the other edges, 5, 3, and 2, which are smaller. So in a minimum spanning tree, you care about overall the total sum, whereas for shortest paths, you care about for each pair, what's the shortest way to get there. So there's kind of a bias. For the shortest paths, you're biased towards things closer to you, because each individual node has its own independent shortest path. Node U doesn't care about how short the path is for other nodes. It only cares about how short the path is to itself. Whereas for minimum spanning trees, everyone kind of collectively works together to get a total minimum distance. So that's why these two things are generally different. You could think of it as people competing versus people collaborating. You're going to get something better overall. I actually really like that. I'm going to write that down. So this is like collaborating versus competing. Okay, so our goal is to figure out the shortest path tree, or equivalently to figure out this distance function. That's what we want to do in this problem. So this is the general strategy. So just like for minimum spanning trees, there's a general way you want to do it. So the first thing is we're going to create this distance function. And the distance function is just our current best estimate of the shortest path from S to V. And we're going to just continually improve our estimates until eventually they converge to the true shortest path. And I'll always use d of v to mean the true shortest. This is the true distance. We're also going to keep track of these predecessors. These are very useful if you literally want to make the tree, but otherwise these are just extra things you don't have to worry about. And initially, we're going to set the distance of v to be infinity for everything. So just the worst possible distance. Now, the general algorithm is going to be relax tense edges and just keep doing that forever. So that's the entire algorithm. While there's a tense edge, relax it. So what does it mean to relax it? So relaxation means we have the following. So UV is tense. Well, let me write it like this. U to V is tense. If the distance of U plus the weight UV is smaller than the distance of V. So what is this saying? It's saying our estimate is outdated. So this implies an outdated estimate. Why? Because we know the path from S to U plus the edge U to V is a path from S to V. And we know the length of that path is at most the distance of U, which is our best estimate so far, plus the weight of that edge. And we know that's smaller than our current estimate of distance of V. So if we wanted to be more accurate, what's the best distance of V currently, then we're going to have to set the distance of V. We're going to update it to be the distance of U plus the weight of UV. And this is called the relaxation. So we've just improved our estimate. We've made it smaller. It's called relaxation because if you think of the edge as like a bridge holding up a giant number, like a giant brick that's just really heavy, what we've just did is realized the brick was much lighter than we thought it was. We've decreased the burden on that bridge, and so it's more relaxed now. I don't know why they originally thought to call it this, but that's the reason they give. So that's what relaxation is. So now what's this full algorithm? We loop through every edge. If we find a tense edge, we update it, which means we've just improved our estimate of the distance. We're just going to repeatedly do that and hope that they converge. We just hope distance of V converges to d of V. That's our hope. Now, it turns out it will. Now, proving it's pretty difficult. There's like 4 giant lemmas you have to prove. This is just one of them. But I will give you an idea of why this one works. So if no edge in G is tense, so assume we've actually been able to relax everything. And remember that relaxation can cause other things to become tense. So if you relax one of these edges, so now this has a better distance. So if you decrease the distance of U, well, that's going to improve the distance of everything that leaves you. All of these distance of V's now need to be relaxed also. So whenever you do a relaxation, you could cause other nodes to now become, other edges to become tense. So it's not usually as straightforward as relaxing each edge once or something. You might have to relax the same edge many times because things keep getting updated. Anyway, so to prove correctness here, we're going to assume we're finished. There's nothing tense. And now let's consider some shortest path from S to V. So the picture here, assume that is the shortest path. Let's say this is the shortest path. And inductively, let's assume that the distance of U is truly the correct distance. So if that's the shortest path, and the distance of U is correct, the fact that the edge is not tense implies that the distance of V is equal to the distance of U plus the weight of UV. But this will also be equal to d of V. If it wasn't, that means distance of V is outdated. But if it was outdated, this edge would be tense, which is the contradiction. We're assuming nothing's tense. So if nothing's tense, then, and using induction, then we have the shortest path for V is correctly stored in that parameter distance of V. Okay? So we're just relying on the fact that the shortest path of V includes the shortest path to U as like a subpath. And then because the edge is intense, we correctly get the full path. So simple induction proof there. There's 4 others you have to do that I will not do. But this is the idea. You can do something similar for all of them. And so because of this, if we are able to eventually relax everything, then we know we're done. It's actually correctly computing shortest paths. Okay, so now let's look at a specific version of that general algorithm of relaxing all the edges. So what's the idea behind Dijkstra's algorithm? It's basically just going to be a BFS. It's a BFS with weights. So whereas the general strategy will allow you to relax many things over and over again, what we're going to do is when we start at S, we're only going to relax things close to S. So we'll start with these 2 edges and so on. We're going to slowly grow our shortest path tree. And so for the same reason as BFS is correct, we would hope that these shortest paths will be correct because they're physically closer to S. There's fewer options to get to those nodes. And in particular, what's nice about this strategy is you would only have to relax each edge once because you never have to go back and update something. You've already perfectly updated everything close to S, and you're just slowly growing out. So if this works and everything's good, then it'll relax very few times. So formally, the algorithm, you're running a whatever first search with a priority queue. In the book, this is called best first search. And the priority is on your distance estimate. So when an edge is touched, when you reach an edge, you're going to relax it immediately, and you'll update distance of v in the priority queue. Okay? So the next node we're going to pop off the queue is going to be the one that's closest to S in total distance. We always prioritize the things that are shortest so far. And just like BFS, this will grow in like waves. So here's the actual pseudocode. So the first thing we do is we're going to insert every node onto the priority queue with its tentative distance, which at the beginning, these will all be infinity, other than for S. So distance of S will be 0. And then while there's still more things to take off the queue, we take a node off the queue, and for all the edges leaving U, all of these, we're going to relax all these edges. Now, after we relax an edge, by definition, relaxing improves that distance estimate. So now we have to update the queue. Because some of these nodes might have way shorter paths now. Especially at the beginning, you start by assuming it's infinite, and now you might have decreased it to like 6. So you need to tell the queue, hey, this is actually shorter than I said before, so that in the next iteration, that might be the next thing you pop off. Okay? So that's the whole algorithm. It's a pretty simple algorithm. So what's the running time of the algorithm? It's this thing here. So we're assuming here a priority queue is going to take log v time to do stuff because you have possibly every single node in the queue. So log v. And you're doing an extract, so that's log v, to do extract of v. Then you have a log v to do the decrease key. And you might have to decrease key for every single neighbor of v. So for every single v, you extract it for log v time, and then you might have to decrease the key degree of v many times. So if we unpack that summation, that's going to be v log v plus e log v, because remember, the sum of the degrees of a graph are going to be twice the number of edges. But again, I'm assuming here that e is pretty large, and so we can ignore the v log e part. And so the final running time is O of e log v. Okay? So that's the pseudocode, pretty pretty simple. We just relax things right as we see them, and then we never relax them again. And because of the order we choose to relax them, this will actually be correct. So in the example above, we start by relaxing edge 4 and edge 3 right here. So now the distance of node 4 is 4. So 4 is indicating that node's tentative shortest path. This one's 3. Then next, we're going to do the same procedure on 3. So from 3, we consider relaxing this edge, but we realize 3 plus 7, which is 10, would be worse than the current shortest path, which is 4. So we don't do anything to 4. But we have a new shortest path estimate for this node here, which is 3 plus 12, which is 15. So now our priority queue compares 4 and 15. Of course, 4 is smaller, so now we're going to move to 4. And from 4, we're going to relax all of these edges that leave 4. So we do that. We get this new distance, 7. We also get a better distance for this node. So here, the previous one was 15. But now we have a better option. Instead of that, we can move from 4 to this node to get a total distance of 4 plus 5, which is 9. So we've relaxed this node, and so we've done a decreased key in the priority queue. These things in red are always the things on the priority queue. And so on and so forth. So that's how Dijkstra's algorithm actually looks like if you were running through it. But the idea is we're just going to greedily choose the smallest thing in the queue, the smallest distance, and immediately relax its outgoing edges and recurse. And it's pretty fast. So any questions on, yes? We don't, there are cycles like general cycles. We are assuming there's no negative weight cycles, but I'll talk about that in a second. But Dijkstra is a general method. It works for any graph. It doesn't have to be a DAG. Just like in this picture here. So in this picture, there are cycles. But cycles don't matter here because you're going to relax every edge only once anyway. You'll never get caught running around a cycle. Okay. So being that this is a greedy algorithm, we need to formally prove it's correct. So let's do that. So as usual for most algorithms problems, you have some kind of notion of progress. And usually your notion of progress is either getting bigger, you're getting closer to a max, or it's getting smaller. You have fewer things you need to process. So here, for Dijkstra's algorithm, our measure of progress is the distances considered. So if G has no negative weight edges, consider each iteration. So on the ith iteration, let's say the node popped off was ui, and the jth iteration, it was uj. Then we want to prove that the distance of ui is smaller than the distance of uj. So things that we pop off the queue later must be farther from S. In particular, it's not just the distance, it's actually the d value. The true shortest path is smaller. So we're continually looking at farther and farther nodes as we continue the process, which is intuitively what we thought was happening. But now we're going to prove it. So it suffices to just look at consecutive nodes. So let's look at ui and ui plus 1. So iteration I plus 1. And the idea here is, well, there's two cases. We either relax that edge or we ignored it. If we did relax that edge, ui plus 1, then by definition of relaxation, the updated weight is this. So that's the updated weight. So we define the distance of ui plus 1 to be the distance of ui plus the weight of that edge. And because the weights are non-negative, because this is at least 0, the total distance must be at least distance of ui. So this is why negative edges are important. If that was negative, it could actually go down, and that's a problem. But because they're positive, we can only make the distances worse than the current nodes. Okay? So if we relax it, we know it'll be larger than the distance of ui because of how we define the new distance. Otherwise, if we didn't relax it, either it was because ui does not change. So in other words, if ui does not get relaxed, this edge can't be relaxed. Or it did relax something, but it did not relax that specific edge. So either way, the distance of ui plus 1 does not change. So what do we know? Well, we did an extract min, right? So based on the priorities, because we picked dist of ui first, we know dist of ui plus 1 is at least the old dist of ui, and this is possibly larger than, so this is old, this is the new dist. So at the very beginning of iteration I, we took ui off of the queue, so its tentative, its estimated distance was smaller than ui plus 1's estimated difference. And then we possibly improved its distance. We made it even smaller. So in particular, distance of ui plus 1 has to be larger than the new distance of ui because it was even larger than the worst old distance. So in either case, the distance of ui plus 1 will be at least the distance of ui, which is what we wanted to prove there. And again, the critical part is that the weights are non-negative. And so relaxing doesn't drastically improve the other nodes' distances. So analogy to BFS that says that the second you touch the node for the first time, that really is the shortest path. You won't later find a better one. That's the equivalent idea. So any questions on this proof? Okay. And overall, this is by induction on I. The base cases are for, you just look at the distance of S and so on. At the beginning, the distance of S is 0. The distance of anything else is infinity. So it's clearly true. So the next thing, and this is important for the time analysis, is each vertex is touched only one time. You only extract it one time. I use that in the time analysis. Because if that node was touched, e times, then that should have an e there. But I said it was only one. So why is this? So we already know the distance of ui. The distances grow over time. So what does it mean for a vertex to be put in the queue twice? That means you put it in the queue, you improved its distance, and then you took it off the queue and you did it again. You improved its distance so much that it had to be put back on the queue. So why is this a problem? Well, according to this lemma, the distances are always growing. So the very first time you change the distance of v, so the first time it's extracted, so let's say ui equals v and uj equals v. So you've popped it off twice. Well, immediately this implies that the distance of ui is at most the distance of uj, and these are both v. So your distance got worse, and so it had to be put on the priority queue. That's the only way this could happen. So implies your distance got worse, which is a contradiction. So it can only be put on the queue twice, it can only be extracted twice, is if its distance got worse due to a relaxation. But by definition of relaxation, you don't relax an edge unless it improves your distance. So that can never happen. And then the last thing, this is basically the same proof from before, just with a little extra sugar. So this theorem just says Dijkstra overall is correct. It's going to compute the true correct distances. So the proof, again, the only difference here is you're going to fix a single path, V0 to VL, which is here. And we're going to prove by induction that every subpath has the correct distance. So the distance up to Vj is at most Lj for all j, where Lj is the length of that subpath. Okay. So the proof by induction, straightforward. The length of the path from S to Vj is built from the path from S to Vj minus 1 plus the final edge. So the total distance is this thing plus this thing. Now the induction hypothesis says distance of Vj minus 1 is at most Lj minus 1. So we just plug that in, and then when we sum these two up, by definition that's Lj. So very, very straightforward. Now the only other part is how do we know the distance is smaller than that? Well, that's because of relaxations. So if we did relax the edge, then we know the distance of Vj either is equal to the distance of Vj minus 1 plus the weight of j minus 1 to Vj. That's if we relax it. So if we relax it, this is equal. Or the distance of Vj is actually better than that. We already found a better path, in which case it's less than or equal to. So in either case, it's at most the length of this subpath, and then by induction, we know this length is small. So that's why that's true. So this is basically the same proof we've seen already. The only difference is we're looking at a fixed path instead of the best path. So this proof holds for any path, any fixed path, V0 to Vj. And so particularly, we can specialize that arbitrary path to be the shortest one. So if you just choose V0 to Vj to be the shortest path from S to V, well, that implies the distance of V, estimate, is at most the distance, the shortest distance to V. So in other words, what Dijkstra is really doing is it's kind of trying all possible paths, but it's doing it greedily. It's skipping paths that it knows can never be the shortest. It completely ignores them. But overall, it'll give you the shortest path. So that's the full proof of correctness. The main ideas, at least. So in each of these, you're inducting on a different thing. So here you're inducting on the length of the path, whereas here you're inducting on the iteration number. Because in each proof, your notion of progress depends on a different structure. So I just wanted to highlight that. But they're both by induction. Okay, so now what if the graph has negative weights? So if the graph has negative weights, Dijkstra still works, but its running time is now exponential. It's really bad. So don't use Dijkstra if there's negative weights. That's all you need to know. So when there are no negative weights, it's really fast. It's O of E log V, which is the same running time for computing minimum spanning trees. So that's about the right amount of time complexity. We probably can't do much better than that. But when there's negative weights, we can probably do better than that. So how do we do better than that? By using dynamic programming, of course. So how are we going to do this? The idea is really simple. We're just going to relax all the edges and then recurse. So in loop form, while there's still a tense edge, we will relax them all. So notice this loop is over every edge. It's not just over edges touching a certain node, like usual. Okay? So why is this algorithm correct? Well, it's definitely going to relax all the tense edges, so that's why it's correct. But if you remember, we solved this using dp. We constructed this thing di of v. So what was di of v, if you don't remember? So di of v, this is the length of the shortest S to V path that uses at most I edges. So it's computing shortest paths when we have a budget on the number of edges we can use. And the reason why we want to do this is because it's capturing our measure of progress better. So in general, because we have cycles in this graph, we can't just allow I to be arbitrary, because it'll just keep going around the same cycle many times possibly. We need to have a cap on the number of edges we're using. The also benefit to doing this is it's easy to do recursively. You just take the number, so it's basically di minus 1 of u plus the weight of uv. You're taking the max of this and d of I at most I minus 1 of v. So either you take the edge, uv, or you don't take any edge. You just decrease your edges by 1. And we talked about that extensively in one of the past videos. So that's what that is. Now, why do we care about it? Well, because of this lemma. So for every vertex v and non-negative integer I, after I iterations of the main loop, we know that the distance of v is at most the I distance of v. So every time you're doing this, really what you're doing is you're increasing your I budget by 1. You can think of this algorithm as you're starting out with no edges allowed, and then at each time you're saying, okay, I'll allow my shortest path to have 1 edge. So first iteration, you allow 1 edge. Second iteration, you're allowing 2 edges. So each time you're doing these relaxations, you're implicitly allowing more edges in your shortest paths considered. So that's why that lemma is true. You can prove it's correct by induction. It's very similar to the other ones, so I won't go through it, but you can read it in the textbook. But this is why the algorithm's essentially working well. Our measure of progress is allowing more and more edges. So at the end, how many edges could we possibly use? Well, at most v minus 1. And that's just because you could have like this kind of path. You could have a path that touches every single node. So if you have n nodes, that's n minus 1 edges. Okay? So the very longest path you could ever have has only n minus 1 edges, or v minus 1 edges. So after v minus 1 iterations, you should be done. You've considered all possible shortest paths. But you could still have tense edges. So this is an important point. So it is true after n minus 1 iterations, you would have created the shortest path, but not the shortest walk. So remember, there's a difference between walks and paths. If there's a negative weight cycle in the graph, then the optimal thing to do is just to keep following the negative weight cycle infinitely many times. Because every time you go across the cycle, you're getting a net benefit. So why would you ever stop looping around the cycle? So in that case, when there's a negative weight cycle, you would want to use more iterations. But that's actually a cool thing. So the idea here is this algorithm tells you two things. It either gives you the correct shortest paths, or it tells you, it detects that there's a negative cycle in the graph. So that's the overall algorithm. You only have to do it v minus 1 times. And then either you're done and you have the correct Ds, or there's a negative cycle, and so it's impossible, at least in sub-exponential time, to compute the shortest paths. So the other case is it's impossible. Okay? So we're not really fully solving the problem because the problem's too hard to solve, but we've at least given you some extra info. So either I do solve the problem correctly and I do it fast, or I tell you it's basically impossible because there's a negative cycle. And sometimes you actually want to compute negative cycles. So negative cycles can be useful in economic applications because a negative cycle could be like in stocks, it could indicate you could keep buying and selling the stock forever and you'll just get profit every time. So sometimes you literally just care about, is there a negative weight cycle in your graph? And you can compute that using this algorithm too. So this algorithm can both compute negative cycles and compute shortest paths if they exist. So it's very useful because it does both. Dijkstra, on the other hand, it would not detect a negative weight cycle. It would just take forever to run. So when you have negative weights, this is the algorithm you want to use. The running time is O of v times e. This is pretty simple. You have a for loop that's O of v, and you have a for loop that's O of e. Literally, it's not even like kind of O of v. It's just I've looped over every edge. And so it's O of VE in total. Okay, so any questions about this? So in terms of the theory, there's a couple things I left out, like this induction proof, whatever. But the important part is when you're using these algorithms, you should think to yourself, is the graph I'm working with, does it have negative weights? If so, you should be using Bellman-Ford. Or maybe even the problem you're trying to solve is to find a negative weight cycle, in which case Bellman-Ford is definitely what you want to use. So it all depends on your application. So that pretty much concludes the tools. So everything up to this point are tools that you're going to use for graph reductions, which is the most important topic we've covered up to this point. So, what are graph reductions? They are a generalization of DP. Instead of DP, where you need to have DAGs, directed acyclic graphs, graph reductions allow you to have undirected graphs, directed graphs, with cycles, without cycles, arbitrarily complicated. It doesn't matter. So this just takes DP one step further. Okay? So let's look at one example to get the idea. So this is the flood fill problem. So if you ever used Photoshop before or anything like it, this is like the bucket tool where you tap a region and then it all changes the color. So here we hit this pixel, we tapped it, and then the entire region turned green. So how do computers actually do this? So what we're going to do is translate this matrix into a graph, and then we're going to run some kind of graph algorithm on it to find a solution to our problem. So what's our problem? We're given a cell ij, and we want to change the color of every cell of same color it's connected to. So what does connected to even mean? Well, it just means you could take left, right, up, or down moves to eventually hit a cell. So for example, this cell right here is connected. Anything that's blocked by the black borders would not be connected. Now, formally defining connectivity in a matrix to do, like, say, dp on would be a huge pain. But we already know what connectivity means in graphs, so let's just turn it into a graph and see what happens. So how do we turn this into a graph? So what's our graph? Well, obviously the vertices, these are just going to be the cells, ij, I is between 1 and n, j is between 1 and n. Okay? So each of these cells is now a node in the graph. Makes sense. Now what are the edges? When should one edge connect to another? So let's think of an example edge first. So just in the picture, we know ij should be connected to I plus 1j because the thing right under it is of the same color, and you can go down one to get to it. So that's a valid edge. And in general, what you want to do is you have 4 cases. So you have an up move, or a down move, a right move. So this is down, right. You also have left. This one's up, actually. And then left. So these are all the possible moves. And you'll make these moves if you don't fall off the board. So there's a mathematical formula for that. So you would do, say, up if I minus 1 is not equal to 0. In other words, if I is greater than 0. So this is valid if I is greater than 0. That's weird. Let me say I is at least 2. It's a better way to put that. We can go down if I is at most n minus 1. And then similarly, we can go right if j is at most n minus 1, and this is j is at least 2. So under these conditions, we should have these edges. So you could read this as you have this edge if this condition is true. If the condition is not true, you should not add that edge. Okay? But those aren't the only conditions, because we should also consider the color. So I'll just put an and color of new cell equals color of old cell. If we had a color matrix C, then to be formal, this would be something like Cij equals C of I plus 1j, etc. for all of them. So that's how you build the edges in your graph. So each edge in the graph represents a valid connectivity. It represents a valid move you can make while still being in the same region. So this is all a single region. Okay? Yes?
The diagonal elements are also connected.
Yes, but you can... I'm not allowing diagonals here. You can simulate diagonal moves if they're valid. Here, yeah, I wouldn't put diagonals here actually, just because, let's say this one was white, this one right here. Yeah, I wouldn't count that. But you can modify the problem to allow other stuff. This is a very general technique. Okay, so now we have this graph. So what is a region now? What's the graph version of a region? Yes.
Any node that can be reached from any node on the tree.
Well, from a specific node, yeah. Even easier. So this is I should also say, that's a great point. These are undirected edges. I drew them with an arrow, but they're undirected. It's an undirected graph. We don't care if you go up and then come back. They're all the same.
Why would it be specific though? Isn't the point of it to be any one in the region? So like in the graph, it would be all of the nodes in that graph. So it could be any node.
So we want to find everything that can be reached from this specific cell.
Oh,
As in the immediate up, immediate down, so forth. Or
The whole region. So I'm giving you a cell and I'm asking you what's the whole region so that we can paint the whole region.
is that just a connected subgraph?
There's a specific word for it. What is a connected subgraph? A maximally connected subgraph. So this is just one of the components of G. So each region in the original problem corresponds to a component in our graph. And that's just because in our graph, if you started at cell ij, well, you can make down moves, you can make right moves, etc. So if you looked at the reachability, if you ran whatever for search from that node, you would mark exactly all of the green nodes because you can reach them from moving down, up, etc. So this is exactly an instance of, so the problem we actually want to solve is finding connected components in our new graph G. And in particular, this will tell you the connected component, but remember, we can always modify DFS to have extra stuff like a post visit. So you can also make sure when you're doing it, you also are physically changing the color of each cell if you want to. Or if you prefer, you can just compute the component and then separately color each cell. They're the same thing. So I'm just going to skip that and then say what I just said. So that's the problem. So what's the algorithm we're going to use? How do we compute connected components? Generally, it's just whatever for search. So we want to do whatever for search from the node ij. And while we compute that, update the color of the cell corresponding to that node. Or compute WFS of ij, then loop through all cells and change its color if marked. So if the node version of it was marked. So these are the same thing. The only difference is one of them This one's like technically more efficient because you're doing it simultaneously. But it's just a constant difference. Okay. And this is another example where you can look at implicit representations of the graph. We don't actually have to physically create this graph. We can just use whatever for search with the understanding that cells ij correspond to nodes and that these are the valid moves we can make. So you don't really have to even build this graph if you don't want to. This is just a mental representation. But you could also build it. You could directly build it if you want to. It's fine either way. And you can do all this implicitly. If you want to. You don't have to. Sometimes implicitly will be strictly faster. In this case, it won't really be faster, so it doesn't matter. So what's the running time of this algorithm? So what's the running time of whatever for search? So the running time is O of v plus e. But we need to phrase the running time in terms of our original parameters. So in the original problem, what are these quantities? Yep. So how many vertices are there? Exactly n squared. How many edges are there? Well, there's at most 4 edges per node, so it's something like, so let's make it even less than or equal to. So this is 4n squared. So overall, it's going to be O of n squared, which is really fast, actually. So we took this matrix problem that, honestly, if you use dynamic programming, would probably be a huge pain and probably be n cubed. And we solved it in n squared time, doing basically nothing. All we had to do was formulate the problem as a graph. We had some graph representation. We figured out what graph problem it corresponded to. And then we just used the correct algorithm to solve that problem using it as like a black box. We didn't have to create a new algorithm. We just used this one we know works. Here, WFS is our tool. And you can use all of the different algorithms we discussed today as tools as well in this framework. So in particular, this is our first example of like a real reduction besides recursion. And how reductions work is we don't care about how the tool we're using or how the black box we're using works. We only care about its specification. We know whatever for search takes a node and searches things. That's all we care about to make our algorithm work. We don't care about the specific details of how, if it's a stack or a queue or whatever. We don't care. We only care about what it's supposed to do. But we also have to analyze our algorithm in terms of our input parameters, not the intermediate graph parameters. Okay? So this is a general reduction. And as I said before, it generalizes DP because it allows you to solve problems where the dependency graph would not be acyclic. So this is the most powerful technique we have in the course so far. You could rephrase every DP problem in terms of some graph and search it somehow. It's not necessarily easy to do that, but you can do it, which is kind of crazy. The downside is usually these algorithms are slower because you're using a much more powerful tool. It captures more problems, so it's generally slower. But sometimes it's not slower, so depends. But yep, so we'll see way more examples of graph reductions. That's most of the homework. It's also all of discussion tomorrow. It's also basically what we're going to do for the rest of the course, so you'll see plenty of it.